Hi folks, we are on the last new lesson for Unit 4. This is the last type of basic derivatives we're going to talk about. And in today's lesson, we're looking at the derivative of trigonometric functions. So we're going to start off looking at the derivative of sine and cos, and also the derivative of the tangent function. So some things you might need in some of these, just kind of a reminder of the compound angle formulas, sine, cos, and tan of a plus b or a minus b. You don't need to have those memorized for me. I would give you the formulas if they were needed, but you would need to be able to use them sometimes in application questions, and also the double angle formulas for sine, cos, and tan. Remember that there's 3 different double angle formulas for cos, but really they're just the same one rearranged with the cos squared plus sine squared equals 1 identity. So what we want to do, first of all, here's a nice graph of y equals sine x. And I want to figure out what a graph of the derivative of this function would be. So I'm going to sketch that on the same curve, kind of like what we did in the derivative of exponential functions, kind of thinking about what the derivative would look like at each point. Now, I know that at turning points here and here, the slope of the tangent is 0 because it's got a horizontal tangent like that. That would be the tangent at that max, or that would be the tangent at the minimum. So I'm going to plot that the value of the derivative at those turning points is 0. And then the same thing with negative pi over 2 and negative 3 pi over 2. So anywhere that's got a turning point, I'm plotting the slope of the tangent is 0. Then what I'm going to get you guys to do, and I'm just going to put the answers up, but if you figure out, estimate the IRC at that point. Now, very important, you must use radians. Okay, these derivative rules only work for radians, and we're going to kind of talk about why, but it really has to do with the scale of your graph. So if we're thinking about what's the slope of the tangent line, and the slope being like rise over run, if your graph in the vertical is going like +1, -1, and your graph in the horizontal and the x values is going up to say 2 pi. Remember, 2 pi is just a number. It's like 6.28. It's 2 times 3.14. So this has like a certain scale to it. And this is kind of drawn about to scale. Like that is 1 unit, and then that would be about 6 units wide, right? This here is about 6 times that, roughly. If you did this in degrees, you would go 1 unit up, but this whole cycle would take 360 degrees. So if you kept the x and y scales the same, your graph would be very long and very short comparatively, right? If we wanted to use kind of like 1 centimeter or whatever it was. So you wouldn't have the same kind of slope if you were measuring in degrees for your run. So if you use radians, and I want you to just estimate the instantaneous rate of change like you would have in advanced functions. So say, for instance, at 0, we would say the IRC equals about the sine of 0.001 minus sine of 0 over 0.001. And you can do the same thing for pi and 2 pi. And what you're going to get is that the slope of the tangent here at that 0, probably not surprisingly if you look at the graph, the slope of the tangent there is 1. And that looks like it's on about a 45-degree angle. So I'm going to plot that. That would also be the slope of the tangent at 2 pi and negative 2 pi. Those we know because of the periodic nature of this function. If you estimated the slope of the tangent at pi, so did sine of pi plus 0.001 minus sine of pi over 0.001, oops, I need the same amount of zeros in there, then you would get a slope of negative 1, which shouldn't surprise you, hopefully, because we know that the function is symmetrical. So what do you notice if you look at the points that I've plotted there in pink? Hopefully you guys see that looks like a familiar function, and it actually does end up being true that this is the cosine function. So here, the derivative of sine of x actually is cos of x. If we did the same thing for cosine, this one will kind of go a little bit faster because I think it's a lot the same reasoning. We would know, again, at the turning points, the slope of the tangent is 0. So at those maximum minimum points, we get a slope of the tangent that's 0. So I'm going to put all those zeros along. Okay, and because we know that the shape of the cosine and sine graphs are the same, the slopes here where it's increasing would be 1. So I'll plot a 1 there. And the slope where it's decreasing would be negative 1. And everybody, after kind of seeing that the derivative of sine is equal to cosine, everybody really wants the derivative of cosine to equal sine, but it's not quite. What function would that be? It's like sine, but it's reflected. So it's the derivative of cosine is actually negative sine. Okay. So we'll summarize that. So if f at x equals sine x, the derivative of that, f prime at x, equals cos x. And if the function is cos x, the derivative, f prime at x, is negative sine x. And sort of similar to what we saw in the previous lesson when we were looking at the exponential and logarithmic functions, if we don't just have an x in there for our angle, if we had like an x squared or a 5x cubed or something, so we had some function g at x, the derivative here would be cos of that same angle times the derivative of the angle. And for a composite function with cos of something, some function, you'd have the derivative as negative sine of that same function. You keep the same stuff inside times the derivative of the inside stuff. And that'll make more sense, I think, when we see some examples. So looking here at an example of a function where we're going to find the derivative, f at x equals sine of x squared. So that's one of those composite functions. We've got sine of not just x, minus cos of 2x, again a composite function, plus sine pi over 3. We want to figure out what's the derivative of this function. So f prime at x equals, now the derivative of sine is cos. So I'm going to have cos, and I'm going to keep the inside stuff the same. Cos of x squared. But if it's not just an x in there, you have to multiply this by the derivative of the angle. So I'm going to take the derivative of that x squared, which is 2x. Now, I've got minus. The derivative of cos is negative sine. So you obviously could just kind of think ahead and make that a positive. That's okay. I'm just showing all my steps. And I keep the angle in there the same. Then I have to multiply by the derivative of the angle. So times 2. This one's a little bit tricky sine of pi over 3. Is sine of pi over 3, is that a function in terms of x? Does it have a variable in it? Does it have a rate of change at all? No, because sine of pi over 3 is just an actual value. So sine of pi over 3 is constant. And if it's a constant, derivative is 0. So be careful not to get tricked. Sometimes people feel like the pi is kind of like a variable because it's not just a number. But sine pi over 3 is just a constant value. Now I would rewrite this. I tend not to like to have something like that 2x after the x squared because it's not part of the angle, but sometimes it can kind of get mixed up and feel like it's part of the angle, or you might multiply it in. So this is cosine x squared times 2x. I'm going to put that 2x out front and make it a coefficient because I don't want it to kind of get mixed up and feel like it's part of the angle. Same thing with this multiplied by 2. That's not part of the angle. It's multiplying the whole sine 2x. So here negative negative is positive, and then 2 sine 2x. So you could factor this. Typically we are going to want to factor factor all of our answers. Factoring out a 2 doesn't do much. Later on in the later units, a lot of our work with derivatives is going to be finding the zeros of derivatives. So we are going to want to, in general, put it in factored form. So that's kind of a bit of a good idea there. So combining together some of our previous examples and looking a little bit more at what we know how to do here. So y equals cos of e to the x. So we're kind of combining together what you guys did in the previous lesson, because now I've got some exponential functions, which is okay. So I have cos of something. The derivative of cos is negative sine and keep the angle the same. Then you have to multiply by the derivative of the angle. So what's the derivative of e to the x? That's that funny function that has itself as its own derivative. And now I really don't want to get these two mixed up. This is the angle, this is a coefficient. So I'm going to bump that coefficient part out front. So negative e to the x, sine of e to the x. Sort of similar here, y equals e to the exponent sine x. That looks super weird, but it's not, hopefully not too intimidating. So here, y equals e to the exponent sine x. The outer function is e to the x. So remember that when you're doing the derivative of this, you keep it the same, e to whatever the exponent was, then times the derivative of the exponent. Now the derivative of the exponent, the derivative of sine x, is cos x. Okay. The next one, 1 minus 2 sine squared x. We don't know a derivative rule for sine squared, but I do know my double angle formulas, and I know that this is actually equal to cos of 2x. So you may have to do a substitution because we don't know how to do anything with powers of trig functions yet. That's something that we will cover in Unit 5. So if I do a substitution and we've got cos 2x, then we could say dy dx, or y prime, just different notation. And note that I need to keep y equals here and then show that I'm taking the derivative in this next step, because this is equivalent to the original function. Now I'm going to do the derivative. So the derivative of cos is negative sine, keeping the angle the same. Then times that by the derivative of the angle. So the derivative of 2x is 2. And I don't want to leave it written like that because it's so tempting just to make that sign of 4x, but it's a totally different thing. That 2 is a coefficient, so I'm going to bring it out front. Negative 2 sine 2x. The last one, and this one's a little bit harder to identify from the graph. So I'm kind of just going to tell you the derivative rules for tangent. If you've got f at x is tan x, then the derivative is secant squared x. And if f at x equals tan of some other function, same rule again, f prime is secant squared with that function as the angle times the derivative of the angle. So we can kind of take a little bit of a look here and see, does this make sense? So this is tan x. Remember that secant x is 1 over cos. So if I kind of thought, what does that cosine function look like? Kind of like that, right? Kind of keep going. Now remember that when you did reciprocal functions, so when you did 1 over f at x and you thought about what those graphs would look like, remember that you said, oh, okay, well, wherever there's a 0 of the original function, I can't have a value. It would just be an asymptote, right? And then here we would have, wherever there was a 1 or a negative 1, those would be the invariant points. And that this would go up like that. And these would be negative, down like that. And these would be positive, up like that. So this is y equals secant x. You kind of, and you can Desmos this as well. And then this is y equals cos x, the purple. Now, what would happen if you had secant squared? I'm going to find a different color here. If I had secant squared, these look kind of parabolic, right? They're kind of opening up parabolas. And if we squared a parabola, that's a quartic, x to the 4th. And that's still kind of the same shape, but a little bit steeper. What would happen to these ones with a negative, though? Here, where we have negative y values, when you square those, they're going to be positive. So the secant squared is kind of the same shape, but just all positive. This is a very rough graph, but it gives you the idea of the shape. Now, is that what the shape of the derivative here would be? Think about what the derivative would be in each of these cases. Now, first of all, for sure, that's pi over 2, 3 pi over 2, negative pi over 2. So for sure, we've got the asymptotes in the right spot with our secant square graph and the tan. I see that the slope of the tangent, these are always increasing. This is always going to have a positive slope. They're positive, positive. So it's kind of like big, steep positive tangents. Then it kind of levels out to a smaller positive. Then it gets bigger positive again. So that kind of feels like that's what the derivative would look like, right? Big positive gets down to a small positive and big positive again. Big positive down to a small positive, big positive again. Big positive down to a small positive and big positive again. We could estimate the IRC at those zeros, but it is 1. Okay, so this is just kind of a, definitely not a proof, but just a little bit of a visual representation. And graphing these on Desmos would be really nice and accurate, right? If you graphed 1 over cos and then 1 over cos squared, which is the secant squared, and then compared that to what the graph of tan would be. Being able to see and connect the functions and the derivatives together on the same graph is a really important skill. So we've got a couple more examples here finding the derivatives. So my first function, we've got tan of x cubed minus pi over 2. So the derivative of the function, remember the derivative of tangent is secant squared, keep the angle the same. So keep that exactly the same. Then multiply that by the derivative of the angle. So then I'm going to multiply derivative of x cubed is 3x squared, and pi over 2, remember that's just a number. That's not a function. It's just like saying if it was like minus 7, the derivative of that is 0. Derivative of pi over 2 is 0. We don't have anything there. And then again, just to make extra sure that that 3x squared doesn't try to become part of your angle, put it out front because it's not part of that angle in there, and just rewrite that. Next one, g prime at x. So we had tan 3x minus 2 times sine of 4x minus 180. So tan of 3x, I need to keep, whoops, not tangent. We've got secant squared, keep the angle the same. Then you multiply by the derivative of the angle. So your derivative of the angle is 3. Then we've got minus 2. Derivative of sine is cos. So I have cos 4x minus 180. Then keeping the angle the same, then multiply by the derivative of the angle. So the derivative of 4x minus 180 is 4. Pop those derivative of the angles out front because they're coefficients, not part of your angle. So I get 3 secant squared 3x. And then this 4 is going to multiply with the 2 coefficient and have minus 8 cos 4x minus 180. And that's it for the derivatives of our trig functions for now. We will be using these in more complex examples and word problems in the next few units. But if you guys can do these derivatives, that's the goal for this lesson.